Today we are going to start a new point from the chapter the crystalline state, that is Miller indices. We have already seen that in a crystal there is a regular periodic arrangement of points in space, and such type of arrangement is shown in the figure. If we draw, these points are called as lattice points. If we draw planes passing through these lattice points, then these are called as atomic planes or lattice planes. These lattice planes can be drawn as shown in figure. It means that they are randomly oriented. They will have different orientation, and within one orientation there will be a number of planes. It means that in a crystal there are number of planes which are randomly oriented. We know that if we consider distance between two atoms, then this is called as lattice parameter or A. And if we consider distance between two parallel planes, then this distance is called as interplanar distance. If we consider a set of parallel planes as shown in figure, then for a single set of parallel plane, the d value will remain same. Suppose here I have shown such four orientations, then they will have values of their interplanar distance as d1, d2, d3 and d4. It means that their d value will change, but a value will remain same. So, Miller is a scientist who has assigned a single number to define the set of parallel planes by three numbers, and these numbers are called as Miller indices. It is represented by small hkl and they are mentioned in bracket. H defines the length reciprocal of the intercept made by plane along x-axis. K represents the reciprocal of the intercept made by plane along y-axis, and L represents the reciprocal of the intercept made by plane along z-axis. Therefore, what is Miller index? The Miller index is nothing but a three-digit number which is assigned to define the orientation of plane or set of parallel planes. The crystal lattice may be regarded as made up of set of parallel equidistant planes passing through the lattice points, which are known as lattice planes. Then for a given lattice, the lattice planes can be chosen in different ways, and Miller has assigned a smallest three-digit number to define set of parallel planes, and that index is called as Miller index. So let's define Miller index. It is the reciprocal of fractional intercept made by given plane with three crystallographic axes. We know that while defining a crystal, we are considering x, y and z. If a given plane intersects x-axis at some place, y-axis at some place and z-axis at some place, then one can easily define its Miller index. Miller index is given by the three smallest numbers which are inversely proportional to numerical parameter of the phase. Miller evolved a method to designate a plane in a crystal by three numbers small hkl mentioned in bracket, and these are known as Miller indices. This method is universally employed, and crystallography, in order to find out crystal structure, this hkl value is most important. Then such type of one plane is shown in figure. There is one plane and three axes x, y, z. This plane intersects x-axis at twice a, y-axis at twice b, and z-axis at c. Now, how to find Miller index of a given plane? There is a procedure to find Miller index of a given plane. In order to find the Miller index of a given plane, one should have first the intercepts made by plane on three axes. That is, you have to first find the intercept x, y, z of the plane on the three axes in terms of lattice constants a, b, c. The next step is express them in terms of actual units, means how many times of A, how many times of B and how many times of C. In order to find this, we have to suppose we have considered x is equal to p1a is the intercept on x-axis, y is equal to p2b and z is equal to p3c. Then in the next step we have to divide this by A, B and C. It will give us P1, P2, P3 as numerical parameters. And next step is you have to take reciprocal of P1, P2, P3 and it will come out as 1 upon P1, 1 upon P2 and 1 upon P3. In order to convert them into whole number, you have to find out the LCM of P1, P2 and P3 and multiply the reciprocal by this LCM. It will give you a 3-digit number or 3 numbers and these are nothing but H, K, L. It means that you have to multiply 1 upon P1 by L, that is LCM. K value can be defined by multiplying 1 upon P2 by L and L value can be found out by multiplying 1 upon P3 with LCM. And these values H, K, L are called as Miller index. You have to mention them in a bracket without mentioning any comma. This is the simple procedure to find Miller index of any given plane. Then next, we will see one example. Suppose there is one plane which intersects x-axis at twice A, y-axis at twice B and z-axis at C. Now next step is you have to divide this twice A, twice B and C by A, B, C in order to get numerical parameters. So twice A upon A will give us 2, twice B upon B will give us 2 and C upon C will give us 1. Next step is you have to take reciprocal of this 2, 2 and 1. It comes out as half, half and 1 by 1. Next step is you have to find out the LCM of 2, 2, 1, that is denominator and its value is 2. Now next step is take the reciprocal and multiply it with LCM. It will give us value of HKL. It means that H is equal to 2 into half is equal to 1. K is equal to 2 into half is equal to 1 and L is equal to 2 into half is equal to 1. And you have to mention them in a bracket without comma. That is 1, 1, 2 in bracket is nothing but Miller index of a given plane. Then let's see few of the characteristics of Miller indices. As we know that Miller index defines a set of parallel planes. It means that suppose a Miller index is given, then it represents orientation of planes along that direction and for that set of parallel planes d value will remain the same. Then second, suppose there is one plane which is parallel to one of the crystallographic axes. It means that this plane is not going to intersect the axis. Therefore, their intercept will be at infinity. And we know that it is the reciprocal of the fractional intercept. So, if we take the reciprocal of the infinity, it comes out at 0. Therefore, if the given plane is parallel to crystallographic axis, its HKL value will become 0. Suppose I am considering x-axis is parallel, then its value, h value will become 0. Suppose y-axis is parallel, means plane parallel to y-axis, its k value will become 0. If plane is parallel to z-axis, then its L value will become 0. And suppose all, then next, if the Miller index of two planes, there are two planes which are 633 and 311 and their ratio is same, it means that they belongs to parallel set of planes. These are parallel to each other. The Miller indices of the direction are same as that of Miller indices of perpendicular plane to given direction is the fourth property. The next is Miller indices of a plane passing through origin is defined in terms of parallel planes having non-zero intercept. If a given plane is passing through origin, then its index will not be 0. It will have some non-zero intercept. Then next is the interplanar spacing and lattice constant can be found out with the help of Miller index. It means that there is one formula d is equal to a upon square root of x square plus k square plus l square, and if we substitute there either the value of a or d, one can and HKL, one can find out either D or A. It means that it helps to find out the crystal structure of the crystal. Therefore, Miller indices plays an important role in the field of crystallography. So, two important factors one has to remember in case of Miller indices is that suppose if the plane is parallel to given crystallographic axis, its intercept will be at infinity and its Miller index will becomes 1 upon infinity is equal to 0. And suppose a plane intersect x-axis or y-axis or z-axis on the opposite side, that is on negative axis, then you have to find out the Miller index and put a bar on it in order to represent that it is a negative. Its intercept is on negative axis. So today we have seen what is Miller index, what is the necessity to find the Miller index of a plane. Miller index is nothing but a reciprocal of the fractional intercept made by a plane with three crystallographic axes. They are mentioned by small hkl in a bracket. It is universally accepted, and in order to find the Miller index of a plane, you have to take the intercept made by given plane on three crystallographic axes as shown in figure. Then next you have to divide it by lattice parameters, that is a, b, c. It will give you numerical parameters, and after that you have to take the reciprocal of these numerical parameters. This will give you a value of reciprocal of f, and you have to find out the LCM of denominator and multiply the reciprocal with LCM. You will get the whole number. You have to mention the and this is nothing but the HKL value of the plane. The features of Miller indices or characteristics or properties of Miller indices are they represent the set of parallel planes. If a given plane is parallel to the crystallographic axis, its index will become 0. Then if the planes are like 633, 311, it means that if their ratios are same, then they are said to be parallel to each other. It is easy to find out the value of interplanar distance or interatomic distance with the help of Miller indices by using formula DHKL is equal to A upon square root of h square plus k square plus l square. And while drawing Miller planes, one has to remember that if a plane is parallel to any of the crystallographic axes, it will meet it at infinity. So 1 upon infinity will give us 0 index for that axis, and if the uh, plane intersects crystallographic axis on negative side, we have to put a bar on Miller index. Hope you have understood.